Hello everyone. Today we are going to continue to talk about discrete distribution. We are going to talk about AB0 class, and we are also going to talk about AB1 class. So if we have a set of data and we want to decide which distribution fits the data best, there are two ways to do that. The method one is mean versus the variance. This method compares the sample mean and the unbiased sample variance to determine which distribution is the most suitable, as shown in the table below. For Poisson, x is mean is equal variance. For binomial, mean is greater than variance, and for negative binomial, mean is less than variance. So for example, if the sample mean is less than the sample variance, a negative binomial distribution would likely fit the sample the best among the three distributions above. There's no need to memorize the table above, as the inequality are based on the mean and the variance formula of each distribution, which are given in the exam table. This page is just another way to compare the mean to variance. For Poisson, expected value of x is lambda, which is the same as variance. For binomial, expected value is mq, which is greater than mq times 1 minus q. For negative binomial, expected value is r beta, which is less than r beta times 1 plus beta. The second method is the slope of k times pk over pk minus 1. We know that pk over pk minus 1 is equal a plus b divided by k. Therefore, if we multiply each side of the equation by k, you got k times pk over pk minus 1 equal ak plus b. This gives us a linear equation in terms of k with a being the slope. Refer to the exam table and note the psi of a for each AB0 class distribution would be like this. Poisson would have a slope of 0, and the binomial will have a negative slope, and the negative binomial will have a positive slope. Here is also a graph to show this. Therefore, to determine the most appropriate distribution, calculate k pk over pk minus 1 for successive value of k and observe whether they are constant, decreasing, or increasing. We may estimate pk as nk divided by n, where nk is the number of observed k. Then we can multiply both the numerator and the denominator of kpk divided by pk minus 1 by n to get n divided by n times kpk over pk minus 1 equal kpnk over nk minus 1. Therefore, observing the trend of kpk over pk minus 1 is similar to observing the trend of knk over nk minus 1. This saves time because exam questions usually provide the data in counts rather than proportions. Now let's look at example 1. You are given the following auto accident data from 1,000 insurance policies. And determine which of the AB0 class distribution would be the most appropriate model for the data. So first you can calculate the mean which is in this formula, and you can also calculate the variance, and similarly you can see in this formula, you can see that mean is greater than the variance. Therefore, we recommend a binomial distribution for this data. Alternatively, we can calculate k nk over nk minus 1 for each k value. When k is equal to 1, you got 1.7476. When k is equal to 2, you got 1.4986. When k is equal to 3, you got 1.2545, so on and so forth. Therefore, this k nk divided by nk minus 1 decrease as k increase. Therefore, we recommend the binomial distribution because the slope is negative. Now let's look at this example 2. You are given the following accident data from 3,000 insurance policies. Determine which of the AB0 class distribution is the most appropriate model for this data. So we can calculate X bar, which is the mean, to be 0.6993. Then we calculate the square, S square, which is the variance, which is 6.6972. Since these two are very close, it's hard to determine which distribution is the best. Therefore, we try to use a second way to do it. The second way is by calculating the k nk over nk minus 1. So we calculate when k is equal to 1, you got the 0.7. When k is equal to 2, you got 0.6999. K is equal to 3, you got 0.6986. When k is equal to 4, you got 0.705. When k is 5, you got 0.667. Since this value is not increasing or decreasing, it fluctuated around 0.7. Therefore, we believe Poisson distribution would be best for this data. Now let's talk about AB1 class. Often, special treatment must be given to the probability of zero claims, and the three discrete distributions of the AB0 class are inadequate because they do not give appropriate probability to zero claims. Therefore, we adjust them and create the AB1 class distribution. Note that the core difference between the AB0 class and AB1 class distribution is just P0, the probability of zero claims. The AB1 class consists of a distribution for which P0 is arbitrary, but the AB0 relationship holds above 1. So there are two ways to create AB1 class based on AB0 class. One is called zero truncated, the other one is called zero modified. First one, if P0 is set to 0, then the distribution is zero truncated. We'll denote its random variable as NT and the PMF as PMT. If P0 is set to P0M, where P0M is an arbitrary probability and 0 is less than this P0M less than 1, then the distribution is zero modified. We'll denote its random variable as MM and its PMF is PMM. Now let's talk about zero truncated. Truncation means omitting a portion of the data, as the name suggests. The zero truncated distribution assuming P0 equals 0. By doing that, the remaining probability do not sum to 1. If you sum sigma Pm from n equal 1 to infinity, you got it's equal 1 minus P0, which is natural. But last we divide each probability by 1 minus P0 to scale them up so that the sum equal to 1. Then you got the PNT, the truncated version of probability, which is equal 1 over 1 minus P0 times Pm, n is equal 1 to infinity. So in conclusion, for a zero truncated PMF, P0 t is equal 0, and every Pnt after P0 is equal to the regular Pm divided by 1 minus P0. For zero truncated distribution, the mean can be derived as below. So the expected mean of ENT is just the En over 1 minus P0. This applies to all other raw moments. The case raw moment of a zero truncated distribution can be easily calculated from the case raw moment of its original distribution. And we always have this relationship between ENT to the case power and En to the case power. There is no equivalent shortcut to calculate the zero truncated variance from the original variance. The easiest way is just to calculate from the zero truncated first and second moment. Alternatively, you could use a formula provided in the zero truncated subclass section of the exam table. Now let's talk about zero modified distribution. Let Pm be the probabilities from AB0 class and Pm be the probability of the new distribution. And let P0m be equal 1 minus C. So Pmm will be equal to C times Pm over P1 minus P0, which will be equal to C Pnt, and it's equal to 1 minus P0m times Pnt. So P0 plus P1 plus P2 to the end equal 1. This is a simple question, so it will be equal to 1 minus C plus Cp1 times 1 minus P0 according to the formula, plus Cp2 1 minus P0 plus Cp3 1 minus P0, so on and so forth. And it will be 1 minus C plus C 1 minus P0 P1 plus P2 plus infinity 1 minus C plus C 1 minus P0, this 1 minus P0, this and this cancel, so it will be 1. This is just saying this zero modified is very similar to zero truncated, except it has its P0 is a small number, so there's slightly difference in terms of the structure of Pm. So for zero modified distribution, we can also calculate the expected value of Enm to the power case power to be 1 minus P0m over 1 minus P0 times Enk. So it's very similar to previous one, except there's another factor in here. Similar to the zero truncated subclass, the easiest way to calculate zero modified variance from the zero modified first second moment would still be this. Now let's look at this example for distribution from the AB1 class. P1m equal 0.4, P2m 0.2, P3m equal 0.1. For the P0m, we know the P0m can be expressed 1 minus C. Now let's look at this relationship still work no matter it's AB0 class or AB1 class. So from here we can get this is equal half, then P3m, P2m will be equal A plus B half. From here we can get A is equal 0.5, which is greater than 0, B is 0. Therefore, we say it's a geometric distribution. And alpha A will be equal beta, 1 plus beta, 0.5, which will tell us beta equal 1. Now PM P1M will be equal to C P1 1 minus P0 0.4, but we know P0 is 1 plus beta will be half. Therefore P1 will be 1/2. So we can get C is equal to 0.8, and P0M will be equal to 1 minus C equal 0.2. I know my handwriting here is not very clear, so refer to the notes for the calculation if you are not familiar.